started filtering and discuss some that solution. Now in this class, we will study about the type of filters, what are the filters, what's inside this, and how to design it. This is our target in today's class. Okay. We simply take this whole matrix, convolve with this image. Also, sometimes they are called filter, window, template, kernel. Okay, these are the words for this thing. Okay, and the numbers inside will define what will be the output, what is the operation. But also, we stopped at the stage we said, okay, we can also divide this 2D filter into 1D filters in order to reduce the computation, right? And we said, okay, how we can do it? We discussed this thing partially in before classes about the separability, and we said that a function can be written in terms of two functions. So this is called the separable. Okay, not all the filters will be separable. Okay, but if the filter is separable, what I can do, I can apply the operation on row and then on column. Okay, but how? So let's say this is the filter, and this is 2 by 3, right? Two rows and 3 columns, right? So this is the filter, and I can divide this filter into 1D filters. One is column, the other is row filter. And if I want to apply this filter on the images, I apply column wise first, and after that I apply on row wise to get the filtered image. And what is the advantages? Advantage will be the lower computation, and sometimes if both of them are same, then we can also reduce the storage capacity by not storing the whole matrix but the vector. So now how to divide these in rows and columns? We will see this in the next slide. But let's say I divide it, so it's very obvious that if I multiply C with R, I will get original, right? So now for any filter, I need to find what is C and what is R. This is what the unique matrix. This is for any matrix we can do not any. This is what I said it earlier, that not all the filters we can divide into like. There are some properties. If it has these properties, then I can divide in row and column. Okay. So I can just say in general, I can say that W, which is our filter, 2D filter, can be divided into two, W1, W2. W1 is a column vector and W2 is a row vector. Okay. And if the kernel or this filter is symmetric, okay, in which if you shift it, you get the same filter. Okay. So if that is the case, then there's another advantage that W1 and W2 will be same. So the row and the column for that will be same. And this is an additional advantage that we can store it as just one vector instead of storing the whole matrix. Okay, this is clear? So the advantage is to reduce redundancy or reduce complexity, and the other is simplify the storage in case we have a symmetric matrix. Okay. Mathematically, I can say that if F is convolved with G is equal to G convolved with F, because it is a cumulative, right? And commutative. And then we have associative, which shows this. So if we use these properties, then I can say that W can be break down into two filters, W1 and W2. So I can write in this fashion using the separable. So if the filter is separable, and then I can change the bracket to do operation any way I want. For example, I can convolve W1 with the image first and then convolve W2, or I convolve W1 with F first and then convolve W2, or I convolve W1 and W2 first and then convolve with F. These are the same thing. So the operation doesn't matter if I do it first on row or column. Okay. Now, how much computation is saved? I think this is pretty easy to do it. So I will just briefly explain. If I take the whole filter, convolve with this, how many operations are required? The total number of operations, what do you mean by operations? Means that if I place this filter here, if I just place the filter, let's say here, okay? So I have to multiply term. So this multiplication is one operation. How many multiplications we have based on the filter size? And total multiplication will be m and n, right? Total number of multiplication, because this n and this is n.
What do you mean here? M and small n small. Is that one?
N is the capital one for the image, small for the filter. Okay. So total multiplication will be this, and if I do it one vector and other vector using separability, it will be m n, capital M n m, because of the row, plus m n of n. So you see the number of reduction in the multiplication. So you can see that how much it's been reduced depends on this. Okay. So for a kernel of size 11 by 11, this is 5.5 times reduction in the operations. Okay, which is multiplication. And this is how it has been performed. You just take the column vector first, do it in this fashion. Okay, and I showed with the arrows that you have to do it like this. You get the image, and then after that, row wise to get the output. What do you mean?
We are like capital M and are cancelled out by itself. We are left with only M and M plus N.
Yes.
Like the size of the rectangle is different, then that will not make sense.
It will not be different. M on N will be same. M is the columns and N will be rows. So it will be same even if it's separable. Like for example, this is M and N. So this is 3 by 3, right? So it will be split into 2, 3 by 1. Okay. So this is just a numerical example. I think the same example that we did it. Now the question is how to split a filter into 2. Okay, this is one of the questions. So it's very easy, but first you have to check the filter if it can be separable or not. For the separable, it should be of rank 1. What is rank 1? Yes. Yes. So number of independent columns or rows are 1. What it means that, let's say this example, I can say that this is the, if I take any column, I can represent in terms of other. So this has a rank 1. Okay, so rank should be 1. This is first thing. Okay, like for example, this column, if I multiply with 2, I get this. If I multiply with 3, I get this. So it means that this has a rank 1. Okay, similarly, the row wise also you can do it. Now, if you see that the filter has a rank 1, then it's easy. You pick any element in this matrix, okay, and call it E. Okay, let's say any element here, call it E, and find the rows and columns that has that element common. Did you get my point or not? No. For example, I have any element, let's say 4. Say, okay, say what? 4? So I have this 4 or this 4? In the middle? Okay. So I have to find column and row that has this element common in it. Okay. So I have no choice just to find that the the rows and columns are this one and this one. You get my point?
Then you have 0 elements in the matrix, you notice that C. So here 4 is C. Then find vector C and R equal to the column and row internal containing the
element. That element should be there. So the only choice I have is these two. Okay.
But they have another one.
So if you select any other number, then the same procedure will be repeated. But the rows and columns will be different. Okay. So let's say, okay, now I selected this column and this row, right? So my W1, which is the column vector, will be the column of that, the same 2, 4, 8. W2 will be R transpose divided by E. Okay. So this divided by 4. So these are two filters. So one filter will be 2, 4, 8. The other filter, row filter, will be 2, 4, 6 divided by 4. So this is R, this is C. Okay. That's it. Yes. Yes. Otherwise you cannot do it. So you have to select one element. Okay. Now, for example, I select another element. Which one? Okay, I select this one. Okay. I select any element, call it E. Okay, and then I have to find a row and column that has this element common. So if I select this column, this row, then this is common. Okay. This becomes my first C. This becomes C. Okay. And star is 4, 8, 12 and divide by 12. And you can check it by multiplication. You get it. Okay. Now you get the separable kernel, right? Okay. And if you go one step further, and if you have any kernel that is symmetric as well, the two vectors will be same. But here, the good thing is that the only choice you will have, W1 and W2, is the middle one. This one. So this is your C. This is your R. For symmetric one. So symmetric, only the middle ones are the ones that give you the separable. Okay.
I think this is not rank 1, rank 2, right?
No, this should be rank 1.
Because column 1.6 by n, you get the second one.
So there's a column multiplication factor. Yes.
1.6 by n.
You can do it directly. Just divide them. So why we have this factor here? Now see, for every time if you have a kernel or the filter, the sum of the elements should be equal to 1. That's why I divided by this to get sum of elements equal to 1. And what's the reason of having sum equal to 1? Normalize. Yeah, normalize, but why? So the answer is, in the which the values will be from 0 to L minus 1. Let's say 0 to 255. If I apply a filter and if it is not 1, then the values will go beyond 255. So you need to normalize it in order to have the values within the range 0 to 255. Okay? Yes?
But it's not given here, right? Now, so I assume this is to have a number, I don't know, and then somehow it gets normalized. So I submit here times maybe 4.8, not divided by 4.8.
Where?
Yeah, this times 1 over 4.8.
Yes. This is multiply with each element.
Where did this come from?
Okay, if you sum them up, you'll get 4.8. Because I want the sum of all the elements to be 1.
Okay. So normalize them also, and some of them for 1.
Normalization max minus.
No, not that one. No, not that. No, just I want to not by normalization, I mean that sum equals to 1, not that 1 and minus 1.
I thought that Victor, you want the magnitude for, okay.
Not the magnitude.
So I still can have 5 plus 10, 6, and 2, and 10, and whatsoever, but I multiply with the sum of them. So I thought that we have to have point something.
No.
But we don't need to use more than one value. The element should be not in one, right?
Could be 1. Could be more than 1.
So we have an
The sum should be equal to 1. Not forget about the magnitude. Even it can be more than 1, less than 1, no problem. No.
how we can calculate this?
But just sum them up. Just sum this one. This
This
sum.
is the original one or the converted one?
This one. Without it, that is the original one.
Original one?
Okay. Now, okay. For example, did we have this example till now? Okay. Let's say this filter. What is the sum?
This.
I have, if I just apply on the filter, I will get the values more than 255, which I don't want. Okay. So I have to divide by 1 by 6 to normalize it. Maybe I call it normalization. 1 by 6 means that sum should be equal to 1. Okay. If I do 1 by 6 means sum equals to 1. So if I apply here, the value should be between the 0 and 255. Okay. Is this clear? Okay, so let's move a bit forward. See now how to define these kernels. So one way is that I know the mathematical properties of the filter, okay, and then based on that I can define the filter. For example, I know that averaging will give image a blurry look, a smooth look. So based on that, I define my kernel or the filter. In order to sharp the image, I have to inverse. I have to find the inverse of that. For example, integration will make, or the averaging will make my image smooth. So the opposite to this is what derivative, which will make it sharp. Okay, so based on these properties, I can define filter. Okay, now other way is to have the desired property. Like for example, I can take a Gaussian filter, Gaussian function, and try to sample it according to the sampling theory that I did before, and try to find the filter. The third way is either I use a frequency response. I say that this is a frequency response of my filter, and try to convert it into time domain. Okay, now one thing is clear. If you have an image and a filter, I will apply this filter to each point. How to do this? I multiply term by time and then divide. And this I have to do, right? But the problem is the binding. For example, if I put the filter here, some of the part of the filter is outside the image. And we already discussed one way is to make it zero. Okay, but there are some other ways as well. So you see that one is zero padding, the way we discussed before. Consider everything zero, it means that I'm just zero padding it, right? Here. Fine. However, the problem is if I do this, I found there's some edge effect. Okay, because outside is considered zero, suddenly in the image there is some information, so there's some mismatch. So you can see that there's some dark area across this because zero is dark, right? Zero is black. So the other is mirror padding, where the boundaries outside are mirror reflected across the boundary. If you do this, you will see that this is much smoother. However, we will see that it will still have some edge effect. So another way is to replicate. So what is replicate means that the points near the boundaries, I just replicate it across that. And I will give you an example. The third is to truncate it, not to take it. And instead of starting from here, I start from this one and remove this edges of this, which will lose the information. So there's some advantages and disadvantages of this. So zero padding is what? Just padding with zeros like this. Then we have the other one is
so starting from here, that tray will be only used for one edge on. We select the filter 3 by 3.
okay.
So we see in the first corner block. So it will be only one value.
Yeah. So let's say, but if the filter is 5 by 5, then you will have this.
Okay.
Okay. So this is just an example of zero padding that just adds. It depends on your filter. Okay, how many pads you want. Okay. The other is the pixel replication, which will replicate the pixel across the boundaries. Let's say this is 334. So I replicate this one, and the other one is the replication of this one. Then if there's another one, it will be a replication of that one. So this is another way. Now here, if you see, there is some smooth transition, not like previous one, which is just 0 and suddenly it becomes 3 and 13, which will create some boundary effect. So here it's up smoother. And then this is called a pixel replication. And then we have mirror padding, which is similar to the previous one, but just slightly different. Because it's a mirror, you consider this as a boundary, and the other ones should come like this. Similarly here, this one should come like this. And similarly, this is a boundary, so this should come like the mirror one. Okay. So if you see here, still you see some discontinuity, but this one is best because it depends on the application. For the edge preservation, this method is good in most of the applications.
How many rows we go and how many?
It depends on the filter size. Let's say you have 3 by 3, so you only need one. If you have 5 by 5, then 2. If you have 1 by 1, you need one.
You need only one row and one column.
Yeah. This is just an example that okay, if I do 1 by 2 application, you want this and 2. This is just to show you that sometimes you may need it. If the filter is not exact 3 by 3, it can be 3 by 2, or it can be 5 by 2. Okay. So this is some of the main difference between zero padding, mirror padding application is the preservation of the edge, but it also depends on your application. Sometimes one is better, sometimes other is better, and there's some trade-off. Okay, this already we discussed it that near the edges you can have the extended boundaries. Okay, now comes the filter. Okay, so we discussed the convolution. We said that the convolution is actually useful for the filtering operation. The filter should be convolved with the image to get the desired result, and we also discussed about the extension of the boundaries. Okay, so one of the simple filtering is the smoothing operation. How to make this thing of smooth? By just what? By just if I just add all these terms assigned here, right? And if I move it to another position, add all these terms, multiply, and add this term, then add it here. Yes or no? Let me show you some one example. Let's say you have some signal. How to make it smooth? Taking the average. So what I will do, I will assign a window, take the average in this, assign to one value, then move this window. Okay, move this window, average, assign to another point, and similarly move on, right? So mathematically, how I can, using convolution, how I can say this? Let's say this is f. So how I can use the convolution to mathematically say this thing? Okay, this is f. What will be my filter in order to convolve these two to get the smooth signal? I want to do it using the concept that we have studied, which is the convolution of f and w. Okay, so I want to convolve with F and W to get the smooth image, but what will be W to get the smooth image? Okay, let me make it more clear. Let's make it discrete signal. So I have a discrete signal, okay, and I want to take three values. I want to smooth it, right? So I went three values, sum them up, assign to maybe the middle one. Then shift this one to three other values and sum them up, assign to the middle value. And similarly, this will make my signal smooth. Yes or no?
Yes.
Now three. The size, it means the size of this thing is three. So I know that there should be three sides. Now what should be W to get me this operation? If I take W as 1, 1, and 1, yeah, you can scale it by 1 by 3, but, and then I can work with the signal, I will get a smooth one. Yes or no?
Yes, unity function will do this.
Yeah, unit step function. Yes.
Yeah.
Yes. Okay. Fine. If I want to smooth this image, what should be this filter? All ones, right? If I have all ones, it means that if I put it here, I will somehow assign the value here. Take the average, assign here. Again, take the average, assign here. It means that I make smooth images. Okay. So one of the basic filter is box filter, which is called averaging filter. And okay, and this is like this filter. Okay. So if I convolve this filter with the image, I will get the smooth. Yes or no? Okay. So why we need smooth images? One way is to reduce the noise. Okay. And blurring, why we need to blur or smooth? Another way is to in the pre-process steps to remove the small details from images prior to object extraction or the bridge, the small gaps. Let's say there's some gap in the images, you want to smooth it out. And also this is equivalent to low pass filter, right? Yes or no? Because we are smoothing it, when you have more fluctuations, okay, it means that this is high frequency. When I smooth it, it means this is low frequency, right? So I also did the low pass special filtering, and therefore I removed the basically high frequencies. Yes or no? So this is a simple averaging filter, but either I can say 1111, 119, but fly by this or I think. Yes or no? Okay. And this is one of the examples using zero padding. If I have zero padding, how I do it? Put a filter here, just 111. So if the filter is here, you will get 1 plus 4 plus 2 divided by 9. Yes. So if you see this, you will get it. Okay, this is paid for the border replication. Okay, the borders will be different, the inside will be same. And border truncation, and that means that I'm not taking the borders. So what I will do, I will start with this one. I cannot start with this one because I don't know the outside. In the case of border truncation, so I will just take this part. The outer part I will take as is, or just remove it, discard it. Okay, this is there. Okay, so now see the effect of each one. This is truncation. So if you truncate it, you get just the inside image. The outside edge will not be filtered. But if you take the zero padding, you see the zero padding, you have a black effect at the edges because of the zero padding. But if you do during the replication, you see still the edges are gone, but there is still some slight stretching of the edges, which is not required. However, if you do the mirror, you can see that it's like perfectly done. But again, this depends on the application. This might be one of the things that you can consider, but there are some other things that maybe in other applications this might not be. Okay, now this is an image, and if I want to apply the different size of the filters, like 3 by 3, and what is that? All ones, averaging filter. You can call it average filter. You can call it smoothing filter or box filter. So 3 by 3, if I apply 3 by 3, I get a smoother version of that. If I apply 11 by 11 or 21 by 21, you get more smoother image or the blurry effect. Okay, more smoothness is more. Okay, the details are lost, smaller details. Okay, so this again the same different type of filters applied as you go very high, definitely. Okay, and another example, you have a picture, apply this, becomes blur. This is like the same thing in 3D, like the amplitude is also shown. So I think this is just another, because I wanted to put a lot of pictures just to give you a real view of that. Okay, so if you have bigger filter, more smoothing. Any question up till now? Above is just the same thing in 3D. So like for example, 1 is the amplitude. So if you, this is 5 and this is 5 and this is amplitude 1. Okay, so just showing in a different direction just to give you a view that how it will look like in 3D. Okay. How you are looking? This one become more smoother. Okay. This one, yeah, more blurry. So why? Because the size of the filter. Because of the size. This is 3 by filter is just 3 by 3. So what I'm doing is I'm just taking 3 by 3 neighbors. Okay, and here I'm just taking 35 by 35 neighbors, averaging in 5. So that's why this increasing blurriness is basically smooth. Yeah. Yes, and smoother is also the information is smooth is a kind of a positive word, and yes, it's a different. But in image, when I say blur, it's like this, which is more smoother. Okay, because I will lose the details, the small details. Okay,
Yeah, the smaller size filter is better than
you cannot again depend on application. Okay, because sometimes maybe this has an effect, but maybe it's not prominent to my application, so then I have to go to this one. Okay. Okay. Now, why we need smooth? When I'm dealing with the noisy image, so I can say that I can smooth it to get better picture. So now, for example, one of the application of smoothing is demarking, but it will only help when we have the random noise I smooth it to get rid of it. Although there is not very prominent because the size of the filter is very small, but you can always play with this side of the filter, okay, to get more smoothness. So one of the application of the smoothness for the average filtering is to reduce noise. The other is sometimes we don't need the minor details, so we try to get rid of minor details, small details, and for further applications, like for example, object, I need a bigger object in the picture to focus on, so I blur it to remove the small objects, for example. So here I define a kernel with a 3 by 3, all ones, divide by 9. Okay, and then I can wolf or filter to the image with the kernel. This is Python code. Okay, and then I'm just showing this. So you can play with it, making 5 by 5, 7 by 7, and you see this is more smoother with reduction in the noise. So this is the same example again in MATLAB. Okay, you have all ones, and then I use IM filter, image kernel, same. Same means that the output size will be same. It means that I use some padding and then remove the edges to get the same size. Let's say my image is 512 by 512, the output will be 512 by 5. Okay. So anyhow, this is one of the things. Now the start is very basic. Filters that all ones will do the job, right? But can it make sense in a real life? What I'm doing is I'm giving the equal weight to all the pixels that are in the window. For example, if I put it here, I will giving all the weights to all the pixels that I am averaging. Okay, but in reality, the pixels that are near to the original pixel should be given more weight as compared to the pixels that are away. Yeah. Yes. So why not to define something like this? This is the pixel of interest. So I give more weight to it and less weight to it. And similarly, if I have another column, I will give even the lesser weight to it. Yes or no? Okay. This is doing the same job, but it will be the performance of this will be much better than this one. Okay, and we will see. And why I divide by 1 by 16? Because this is some of this should be 1. Okay. Yes. So this is just a box filter, averaging filter. This is also the averaging filter, but weighted averaging. Okay, give more weight to the near pixel as compared to the further one. This makes sense, right? Because near pixel have more correlation, so it will be more weight than the further one. In 1D, if I want to visualize this in 1D, what it will look like? In 1D, for example, the same filter here, but different. You see, it was 1 1 1. Yes. So how it will look like? Yeah. So it means that okay, if I just plot it in 1D, it will be something like this, right? Yeah. Okay. So let's take a Gaussian in 2D and make a filter out of it. This is Gaussian filter. So if that is the case, what will be in the 2D? Just two variables. Here we have one, right? So make it 2 instead of x, make it x y. Yes or no? Okay. Okay. So if I just plot this line, it will be like this. If I plot this line, it will be this. But if you see a smoother one like the Gaussian, you will see a very smooth transition between black and white. This is what I wanted to convey in this figure. If you have a sharp transition, there will be a very sharp here in the images. But if you have a smooth one, it will give you very smooth. So if I have a smooth image, it will give me the smoothness, but that will be better than just using the box filter. So now, as I mentioned, instead of having just equal weight to all the pixels like 1 1 1, I just define a 2D Gaussian. What is 2D? It will look like this. It will look like this. Okay. So now taking any value, how I can find the filter? So it will be what 0 0. What is this? Minus 1 0, right? Yes. And similarly, this will be 0 minus 1, and this will be 0 and 1. This will be minus 1, and so on and so forth. Exactly. So only what I need to remember is this equation. So whatever value I want to find, I will put it. Let's say 0 0. So I put 0 0 here with some k which is known to me according to my own filter design. I put it here to get the value. Now for this example, I took k equals to 1, sigma is equals to 1, and I want a 3 by 3 filter. So I can, if I give you this example, what you will do, you should have just 3 by 3 filter with these numbers, 0 0, minus 1 0, these locations. Put these locations into the here to get the value. 0 0 will be what? Yeah. Okay, and symmetrical. Okay. So once you get this, all these values, put minus 1 0 in this equation, and you will get the value which is equal to this one. Once you get the value, I normalize it to get filtered. Okay. So the same thing in 2D, I can visualize, right? This is 1. You can see, right? This is 1. Okay. So where is point 3? Where is point 3?
And the second December.
This one, right?
Yes.
And this is point 6, point 3. This one. Okay. Similarly, this one, where it is? This one. Okay. So I just wanted to visualize now because later on we do some filtering, so it should be visualized in 3D. Just for visualization. Even if you understand this, it's okay. But I want you to visualize in 3D to get inside what is happening. Is this clear? And this is again the Gaussian filter, but since this is like floating point numbers, okay. So what I can do, I can change them to integers by dividing it by 4. Let's say multiplying and dividing by 4 and rounding it off. So this is again the behavior of this, and this is same. If I multiply and divide by 4 and round it off, I get this thing.
How would we define these two variance and this equation?
Variance, okay, the variance depends on our own spread. See this, variance is 2. So it's like the spread is less. If I make it 5, what is variance? So variance